Today, we're putting on our detective hats to investigate a celestial crime scene, or, well, maybe more of a cosmic mystery. Our case file is on a star cluster, and believe me, the clues are literally written in starlight.
So, our subject is Messier 34. It's this brilliant cluster of stars way out there on the border of the Perseus and Andromeda constellations. And yeah, it looks like this beautiful, peaceful city of stars, but it holds a really complex story, and it's written in a language we're only now learning how to read.
So that's the big question, right? How in the world do we piece together its past, its present, and its future from across this insane ocean of space? How do we even begin to play cosmic detective?
All right, here's how we're going to crack this case. First, we'll meet our subject, M34. Then, we're going to figure out the timeline using a pretty wild clock made of stars. After that, we'll analyze its chemical fingerprint, dig around in its stellar graveyard, and then use AI for definitive roll call. And finally, we'll put all those clues together. Okay, first things first. Let's get properly acquainted with our subject. See, M34 isn't just some random smattering of stars. It's what we call an open cluster. You got to think of it like a family, a whole bunch of stars all born together from the exact same giant cosmic cloud. And now they're all traveling through space as one big unit.
So yeah, these are the basics, the kind of info you'd find right at the top of a case file. But to really truly understand M34's story, where it came from, where it's going, we need to gather some very specific and frankly, very clever pieces of evidence.
Every good investigation needs to establish a timeline, and our first forensic tool for this is honestly amazing. It's a cosmic clock, and it's built right into the stars themselves.
This incredible technique is called gyrochronology. Here's how it works. Think of a star like a spinning top. When it's young, it's whipping around super fast, but over millions and millions of years, its stellar winds act like a brake, slowing it down. So by measuring how fast the stars in M34 are spinning today, we can tell time. It's amazing.
Now, what's really cool about this is how it completely bypasses one of the biggest headaches in astronomy, knowing the exact distance to something. The old methods, they totally relied on that, and they gave a massive age range for M34. I mean, anywhere from 100 to 500 million years old. But gyrochronology, it doesn't care how far away the cluster is. It just measures the spin, period.
And look at this. This just shows you the power of the method. A study led by David James used this technique to absolutely nail down M34's age with incredible precision. 193 million years, give or take just 9 million. Okay, the timeline is officially set.
All right, we've got our timeline locked down. So what's next? Well, just like any good forensics lab on Earth, we need to run a chemical analysis. We got to find out what M34 is actually made of.
By looking at the light from its stars using a technique called spectroscopy, a study by Schuler and his team found that M34 has a totally unique chemical fingerprint. For one, it's a little bit richer in heavy elements, what astronomers just call metals, than our own sun is. But here's a really weird clue. It's surprisingly low on nickel. That unique signature is a major clue to the specific part of the galaxy where this star family was born.
Okay, our investigation is about to take a turn into the past. Because if you want to understand a family's history, you can't just look at the living members. You have to study the ancestors. And in space, that means we have to visit a stellar graveyard.
You see, the biggest, most massive stars that were originally in M34, well, their story is already over. They've already lived out their lives and died. They swelled up, puffed off their outer layers, and left behind these tiny, super dense cores we call white dwarfs. These things are basically cosmic fossils that tell us about the massive stars that came before them.
So, a team of researchers from the Rubin study went hunting for these stellar ghosts, and by carefully scanning the whole area, they found them. They identified 5 white dwarfs that are very likely original first-generation members of M34, which gives us a direct window into the cluster's deepest past.
But hold on a second. All of this analysis, the age, the chemistry, the history, it all hinges on one absolutely critical question. How do we know which stars are actually in the club and which ones are just photobombing the picture?
I mean, just think about it. When you point a telescope in M34, you're not just seeing the cluster, you're seeing it against a backdrop of millions upon millions of other stars in our galaxy. Figuring out who's in the family and who's just a background stranger has always been a monumental challenge for astronomers.
But now we have a secret weapon. We can use AI as a kind of cosmic bouncer. We feed it incredibly precise data about the motion and position of every single star in the area, and the algorithm learns the unique signature of an M34 member. Then it creates a definitive guest list.
A study in 2022 by Noor Mohammadi and his team did exactly this. And the result? Bam! They identified 743 high-probability members, giving us the clearest, most complete census of the M34 family that has ever been put together.
So, after all that digging, what has our cosmic forensic investigation actually revealed? Let's review the case file and put all these clues together.
We know its age with stunning precision, 193 million years. And we know this not from some theoretical model, but from measuring the actual physical spin of its stars.
We know its chemical makeup. It has a unique fingerprint, a little richer than the Sun, but with that weird lack of nickel, which tells us a story about the galactic neighborhood where it grew up.
We've even uncovered its deep history by finding and studying those white dwarf remnants, the literal stellar ghosts of its first and most massive stars. And now, for the first time, we know exactly who's in the family. We have a definitive roll call, all thanks to the power of AI that can sift through millions of stars to find the true members.
You know, by piecing all of these clues together, we've basically written the biography of Messier 34. And every single one of these star cluster biographies, it becomes another crucial chapter in the grand history of our own Milky Way. It's a fossil record, showing us how stars, how planets, and yeah, how ultimately we all came to be.